our last senior thesis presentation. So Henry will close out the show. He is from Knoxville, Tennessee. Also has lived in Connecticut for 12 years. He's a CS major and has happily taken a bunch of varied classes while he was here. And he will be a software engineer, but keeping the option open for eventually going to grad school and especially learning more about AI. And when I asked him about a random fact, he told me that he is pretty enthusiastic about anything he likes, and he often evangelizes that topic. And as an example, he gave that last summer he discovered Vietnamese sandwiches, which I don't really try to prevent. And he said in that week he would have told every single person about Vietnamese sandwiches. So without further ado, let's welcome Henry.
Okay, everybody. I'm really happy to see so many faces here on a warm day in Middlebury. It's great to talk about computers. My project was in part not implementing, but experimenting, in another part just exploring and trying to understand what a generative adversarial network is, and that's a GAN. And just as a preview, this is a painting that one of my networks made, and you'll see a lot of those throughout. So the whole outline here, I'm going to give a little more background on the event, and then I'm going to give learning context so that you can better understand how on earth we might use computers to generate art, and then I'm going to talk about the systems that I actually used to do it. So these are prior attempts at art. This was actually done by 2 students at Williams last year, and they used GANs to generate paintings. They say this is a portrait, but to me, I agree that it looks like a portrait. You can see a head and sort of maybe clothes, but I wasn't totally satisfied with the fact that it was very small. It's only 64 by 64 pixels, and it's just not very detailed. So I wanted to know if GANs could do much better at this task of art generation. So a little game now. Can anyone point out which images are real and maybe if there's some fake ones? So I'll take a guess from someone, if anyone wants to provide a guess.
Top middle is real.
Top middle is real?
Bottom middle's fake.
Bottom middle is fake.
Top right is fake.
Top right's fake.
Okay. Yeah, so top right is fake. That was done at the beginning of last year, maybe a little before. But it turns out that actually the rest are fake too. The one at the bottom was me. But so here's the point. Here's the crazy idea. You saw the not so thrilling art at the beginning, but you've also seen this. So my goal was to use the technology that could make this work to make art that was more compelling. So a little machine learning background just to give a little more context. What is machine learning? I like to think of it as programming computers through pattern recognition. Why does this matter? Well, it works really well for a lot of tasks. Andrew Ng is he's a really well-known AI expert professor. He does a lot of consulting with big companies, and he says that it's the new electricity because of the way you can solve many, many problems with it. So just some examples: spam detection. Is this email spam or not? Product recommendation. What film might you want to watch next? And the rest are self-explanatory. So how does this work? We define functions, and again, remember functions are mappings of inputs to outputs. And so what we do is we define model functions that take in some input. In this very basic case, that'll be x, and then they map it to some output. And for regression, we do that on points that map to outputs in a continuous range. So that's what's going on here. And initially with these labeled training examples, these first 2 lines seem plausible, but given more data, we can see that this red line provides hypotheses that match reality in a much better way. So why is it that the red line does much better than the blue line? Well, it's because its parameters, which in this case are the y-intercept and the slope, better fit reality. They sort of encode the rules that determine this phenomenon. So we can evaluate them too. And the difference in the y dimension between a point and a line is that function's error in its hypotheses. So blue you can see has much more error. And that's a fundamental idea here in machine learning. So we have different ways of representing phenomena. That's the parameters. And then for those different representations, we can evaluate them with cost functions, like error, for instance. But then the cost functions are themselves functions, which you can take derivatives of and do other tricks to, so that you can optimize them. So then at the end, you have a model that all of a sudden is getting much lower error. And in doing that, that's how you learn patterns. And that's how we can train computers to recognize faces or teach cars to recognize pedestrians and so on. So the last example was using a line to explain a phenomenon. In reality, we use much more complicated models because complex models, they can describe a given data set much better because they have more expressive power. They have more to work with, in a sense. So over here on the right, we can see a really complex function, and it looks good because it's perfectly doing its task on this data. And in this case, it's classification. So we're not doing regression. We are simply defining a decision boundary between two classes. So okay, but anyway, this looks like it's perfect, right? It doesn't make any mistakes. But the problem is, this is kind of just a random data set, and there's a lot of noise, and the fear is that this memorized noise won't generalize to reality. So you can memorize specific examples, but that's not useful. And then on the other end of the spectrum, overly simple models, they just don't work too well. In this case, perhaps the parameters that were trainable were y-intercept or something, because clearly, like, it's just not working. So the goal is to have lots of data so that you can get nice generalizable trends. So what is a complex model? Our brains are a complex model. And just as an example of how incredible our brains are, you can actually not train, but parts of the brain that naturally would handle audio signals, the auditory cortex, if fed signals from the retina, from the eye, you can learn to see through those auditory cortexes, which is kind of amazing because evolution has optimized that network of neurons to hear. But all of a sudden, they can learn to see. Relatedly, we use artificial neural networks to model phenomena. And so again, neural networks are still just functions, but they're a little bit more complex. They're networks of neurons, as you can see, where each circle represents a neuron, and each neuron is its own function with its own inputs and outputs, and they too have their own model parameters. And it can be shown mathematically that neural networks can actually represent any function, which is really, really cool. And another cool aspect of neural networks is that you have a lot of freedom in how you design them. So you could have as many neurons as you want in a layer, or as many layers as you want. And you could think of a situation where maybe you would want to have, instead of one number in the output, you could have many numbers, such that you would have enough nodes where the number output of each node could correspond to a color value in a pixel in an image. And so in that way, that's how you might be able to at least get to this sort of picture-like output. And then convolutions are another calculation that are often embedded in these that have taken over a lot of image-related machine learning. So, why is machine learning taking over now, as opposed to before? neural networks have been around for many decades, and machine learning has been around, similarly long. Well, we have better CPUs than ever. We have better GPUs, and those are really important for machine learning. But we also have systems like TPUs, which are applied or purpose-designed neural network processors. We also have better software and algorithms, so advancements through research in deep learning and neural networks have produced really creative models. Oh, great. Okay. And there's also just a lot more data out there. If you consider the product recommendation example, a company like Netflix now, because of how everyone's on the internet using Netflix, has much more data about film preferences than would have been possible to gather before the internet. So again, remember model complexity. There's a lot of power in that, but with that you need to provide data so that you're not just getting fine-grained noise. But we have lots of data and we have lots of models, lots of powerful models, so this idea of deep learning is really powerful. And what deep learning is basically neural networks, but pretty extreme, just lots of layers. And these are taking over. So we theoretically have functions that can model any function. We theoretically have fast hardware, and we theoretically have lots of data. It's a powerful combination, so it seems that we can do anything with a neural network, right? Perhaps, but we still need work. There's still work, because we need to define the model's objective. You need to quantifiably express how well the function is doing at its current task so that it can improve, and it can know what sort of changes to make to improve. So, given the tools discussed, how could you train a model to produce realistic but fake photos of people like we saw before? And to do that, what would be the training objective for such a system? And this is really difficult to answer. And intuitively, this is hard because you would be objectively trying to evaluate a subjective question. Unlike, spam or not spam, well, maybe that's also subjective, but but unlike, an image of a tiger versus school bus, that's not ambiguous. This is kind of ambiguous how realistic something is. So it's very difficult to define these sorts of objectives. So that brings us to Generative Adversarial Networks, or GANs, which Jan LeCun calls the most interesting idea in the last 10 years in ML, in his opinion. And so Jan, he actually invented the convolutional neural network, or popularized that. He also is the chief AI scientist at Facebook, and he created one of the data sets I use. So he's like a giant in machine learning. So that's really high praise from a big shot. Okay, generative adversarial networks again. We can use them to generate novel, realistic data. The focus here is images, but there's nothing that says that they have to be images. You can apply it to other sorts of data. So this is another painting I generated, and for the remainder of the talk, I'll throw a bunch of these in there. But so if you see an unlabeled painting, that's one of the ones I made. But again, these people never existed. Similarly, this guy never existed, and neither did a painter that painted that. But another crazy aspect of this is that the actual component of the network that generated these images has actually never seen a photo. So that'll be more clear soon. But the incredible part is the neural network that is creating this it's not just memorizing. It's doing math to figure out abstract rules about reality, and that'll become more clear. A little bit more. So what's exciting about this? Or what was the core of the idea? Ian Goodfellow describes this as reframing AI and machine learning in terms of game theory. So what does that mean? It means that a GAN is a way of representing a game, a competition between two agents, a discriminator D and a generator G. And still, remember, D and G are just functions, and I put that there just to emphasize the fact that they're just mathematical equations that have inputs and outputs, and they have some structured way of doing what they do. And they have parameters. In practice, they are almost always neural networks. I haven't seen a case where they weren't. Okay, so to better describe their interactions, it's pretty convenient to use a metaphor of detectives and art forgers. So in this world, we have two types of people, detectives and art forgers. The detectives, being the good guys, simply try to determine whether a given painting is real or if it's fake, made by generators. So this is a more straightforward problem than the problem of generation. All it's having to do is to discern between this, and that it gives an output, a probability that the painting is real. So what does the generator do? The art forger is just trying to sell fake paintings and make money. So as long as it can pass off its own paintings as being real, then it's great. What are the inputs to this? It has random noise from a latent space that I'll talk about more later. But basically it transforms random numbers, a vector of random numbers, into some image that hopefully looks like a real painting, which is then one of the inputs to that. So the core idea is that they're competing, and in their competition, they learn. So it's very computationally expensive to do this. In the Williams example last year, they had only a 2 gigabyte GPU, which was a major limitation on their system, or on their experimentation. And that's why they could only get output that was 64 by 64, which is less fun than bigger images. So I used our Gattaca computer here, which has a Titan XP, which has 12 gigabytes of RAM on the GPU. And that's a pretty serious piece of hardware. And so that's what generated these two, and that took 8 days, 13 hours. The team at NVIDIA, they generated this guy here. Being at NVIDIA, they obviously had good GPU access, and so they used 8 V100 GPUs, which are $10,000 to $15,000 a piece. So, and that took 2 weeks on that. So this is kind of a crazy process, but it's really powerful and interesting. So what is this process? Well, again, it's training. D, if we go back to the structure of the system, it's actually a supervised learning problem. Because of how the GAN as a whole is organized, every painting or every fake person or every input that goes into D, the detective, the discriminator, we know the outer loop knows if it's real or not. So it can train that in a straightforward way that's been done a million times. And it uses the cross-entropy loss function in many versions. So the problem before, what I was trying to motivate here, was that training G was kind of a weird problem, because we're trying to answer a subjective question with, a harsh, objective mathematical expression. But now, if we don't just say to the generator, make real art, but rephrase the problem as trick this guy, which is just a mathematical function, it's a bit more straightforward and it's easier to work with. So now we're rephrasing the goal. The goal of the generator is not to create real looking art, it's just to mess up D, and J are the cost functions. So again, you want a low cost function. You're moving to lower measures of your error in training, and so what G tries to do is just to mess up the discriminator. And then doing that, art can come out of it. It's incredible. There are other formulations of this game, because this actually does have a few issues, but we don't need to get into that. So what this converges to is a Nash equilibrium, and this is another idea from game theory. And a Nash equilibrium is a situation where you have two players who are facing off, and they each have strategies. And in this case, strategies are model parameters. If we go way back, it's like the slope or the y-intercept. It's the way they do what they do. And so a Nash equilibrium is a situation in which you have two players that are facing each other, and neither is incentivized to change what they're currently doing, so they get to this sort of point where they're stuck. And doing this crazy math, they proved that in some cases it can actually converge at a point where the generator's output is realistic, and it does stuff with probability distributions, and I can talk about that later after this if you want. But remember, G never accesses real data. So Z is latent space, random noise, and as you can see, G is never called on X, which is real data, if you're curious to see that. Now, they're not perfect, and this work I'm doing here isn't perfect. For instance, so these are bad, right? I actually think they're very cool. But you can't just say that they're good or bad because they're paintings. And we get back to this subjective idea. So, but my point here is that evaluating how good a GAN is difficult. I can say, it's easy for me to say, okay, I have bigger output than the people who did this last year, but I can't say that my paintings are like better. That doesn't make sense. And then just more practical issues, mode collapse. Often a generator will find a winning strategy, and so what that means is it might just make 1 million of the same painting for all of the latent space. And then training stability, as you can see, it doesn't always work well and things go crazy. So what did I do to get these results? I used the code from the team in NVIDIA because, again, it was pretty good. And then I ran it on the MNIST dataset, some paintings, and I've also done it on X-ray images. And then I used the second GAN, because GANs are cool, to upscale the output, and I'll talk about that part later. So again, just the GAN idea here. We have the discriminator taking an input and gives yes or no, and then the generator transforming random noise to some sort of output which is hopefully going to look real. So we all know what handwritten digits look like, but this is the extremely commonly used data set for computer vision problems. Each one's a 28 by 28 image, and this was done by Jan, who was the guy I quoted before. So I used the progressive growing approach from the team at NVIDIA. And so what you'll see is that it starts out with really low resolution and then it gets sharper. And the idea is that it's easy to learn simple patterns and then you build off that to work towards more nuanced patterns. So initially, the output is random. That's before it's learned anything. Almost immediately, though, it realizes that the images are predominantly black and that there's, varying amounts of white and gray in the middle of the images. And then later, you can sort of get more into number-like shapes, and then eventually, it's basically indistinguishable. So let's look at the painting version. These are human-made paintings, and it's really refreshing to see these after looking at like thousands of mine. So here we go. Remember, random noise initially. Then we're at low resolution. Basically, all it's figured out are the sorts of colors that are plausible in paintings. But then it soon finds out, what kind of shapes a human might look like. And I put in exclusively portraits because I think working with faces was interesting, and looking for faces and things is kind of a human instinct, I feel. So that's that. And then it gets sharper, and then it gets a little bit better by the end. This was probably my favorite one. I just thought it was pretty. So there's kind of crazy stuff going on with the latent space. And because these are functions, well, not because, but these are functions. So remember, there's inputs going to outputs. Latent space is the input. So in this case, you might have 3 numbers. And if you subtly change inputs, the outputs slowly change also. So that lets you interpolate between various vectors. So that's what is going on here. And that's why there's a smooth animation. We're slowly changing the inputs to the generator that created these. So that's fun. But there's also another like magical property to the latent space and the way the generator treats and works with the latent space. There's a bunch of weird properties that a lot of different models take advantage of to do different things. But this is a fun example. So this team used GANs to generate lots of human faces, and they took the average of the inputs that generated these examples here. And so think of this as men with sunglasses. So that's the input. And then they took the average input of the men, and that's the second, that's B. And then they took the average input that generated women, and that's C. And if you do men with sunglasses minus men plus women, you get women with sunglasses, which is crazy because all of a sudden you have some encoding or some sort of logic in there that is dealing with sunglasses, but we never told it what sunglasses were. So that's the incredible part. You can do other mappings with this latent space information. You can provide other inputs. And so that's what allows these crazy things on the right here. That's pix to pix. You can also do super resolution. So that was SR GAN, and that's what I did earlier. But you can also give text. So you could say this bird is red, and then you get lots of different red birds, where different birds correspond to different latent space entries. You can use it to enhance other machine learning. There's this process called semi-supervised learning, which basically uses a GAN to train a very good detective, good discriminator, and then you can use that discriminator as a really effective classifier, and the whole process requires much fewer labels. You can also use it to enhance training data. So it's not uncommon to use synthetic data. You can use a conditional GAN to improve it. So conclusions. They have imagination in the sense that they can create vast amounts of novel examples. Awareness, I say, because they become aware of these features which aren't labeled, like this frame painting, for instance, or the sunglasses. More broadly, this shows me that interactions of neural networks are very powerful, but much remains to be improved, and humans are much better. And so what I've started and what I'll continue doing is working with X-rays, because I think that's an interesting problem. So thank you, Professor Sharstein, for much help. Thank you, Professor Lenderman, for Gattaca help. Thanks, Pete, for GAN discussions. And now this is just a little side bonus. So latent space through the paintings. Okay, and thank you very much.
You can either watch this or ask questions or do both at the same time.
Yeah, I can pause if need be, but yeah, Limbus.
Yeah, I have a question about training. So how do you tell the machine how close is the painting to a human? Because you cannot tell like it's a human or it's not a human. There's a scale of similarity. So how do you tell the machine?
Do you mean the output of the generator? How do you?
Yeah, the output of generator. How do we tell the generator like this is kind of half human?
Okay, yeah.
This is close to
Yeah.
This is not.
Okay, so you're right. That's the problem with the kind of like weird, it's hard to define that. So that's where the discriminator comes in. The discriminator, the detective, is what's making these yes-no decisions. And that is just a more classically trained machine learning model. But based on that you can think of that as an adaptive loss function. And so that's where all the like decision making comes from related to that question. I don't know if that was helpful.
Relating that question, for the error function for the output of your generator,
Yeah.
that's, you basically just get like per input errors from the discriminator through backprop, right?
Mm-hmm.
Cool.
So
And then that is like your per output error
Yeah.
from.
basically how confident the discriminator is that it's fake is bad. You want it to be
Right.
you want it to be very confident that it's real, and how far away you are from that is error.
Right, and with backprop you can get that for each
Yeah.
input bit.
Yeah, and that's how that works. Yes, Peter.
It does seem like different latent space would give you different kind of output at the end. So how do you randomize the latent space?
Okay, when you say randomized latent
Like,
space,
What is you would ideally want different kinds of latent space that you give to a generator to see what kind of output you get from it. There maybe
I don't know what you mean when you say kind of latent space.
So like it's like the initial state of the data, right? And then the part where you talk about the man with sunglasses.
Mhm. Yeah, yeah.
And then there are different components to the latent space that
Mhm.
lead to different results. So how would you say like another machine learning algorithm that would help you determine the best latent space for your purpose? At the end, is there any technical?
Okay. So the latent space, I wouldn't say that there's like a best latent space. It's kind of this random noise that we can use as input to generate novel examples. So if I had this box here, chalk anywhere? Okay. And I just give it a number, like X, and out pops, we'll call that G, and out pops a painting. The latent space is basically just some number. And so you could give it 1 and it would give you some painting, and you could give it 2 and it would give you some other painting, and you could give it 3 and it would give you some other painting. So the sunglass example is it was looking at a lot of examples over here, grouping them here, and then going back just to see what gave it. But when you're training, you sort of go over all of it. It's just kind of crazy. Yeah, you're sampling from a probability distribution, multi-dimensional Gaussian.
So at 8 days, if you reach equilibrium, what everything's not really improving, or if you give it another 8 days, you think you have like museum quality. Well, not that these aren't museum quality.
So it's funny you ask that because if we go back to this one, this was actually, so the whole process here when we were moving through this was 8 days, 13 hours, 27 minutes. This was actually at like 8 days, 3 hours. And I thought the later examples looked a lot worse. And that's why I didn't put them here. But it's kind of weird because sometimes you'll get like, you know, that half of the face looks pretty good. And sometimes you get lucky and both halves look all right. And then all of a sudden, randomly, you'll get like just a mess going on that doesn't even make sense, like that will just pop up on what would have been a nice face. So I don't think it would have done much to keep going.
But if you have more examples of real people?
I think that's a huge, that would be very helpful. So I had 15,000 portraits, and they were widely varied. Looking at the data set, one of the portraits was a foot. So obviously a foot isn't too helpful to this, but it represents the problem that unlike the celebrity data set, Celeb A HQ data set that the NVIDIA team used, these are really not, like pretty poorly standardized, and so that's why there's like so much crazy variation. That's why this one randomly has a picture frame, and this one randomly is in a circular shape of some sort. And there's different perspectives too, and different sizes. And so just having standardized data would have made it more helpful. But that's why I'm exploring X-rays, because I have a data set of 112,000 X-rays from the NIH. And these are much more standardized images, sort of like a photo. There's more strict rules that define what could come out of an X-ray. Presumably there's like bone shapes and whatnot, whereas a painting is it's kind of more free if you think about it. So my hope is maybe in like, I don't know, 8 days or 20 days, that this will be really, really good.
What are you trying to do with the X-rays?
So the first goal is just to make outputs that look super, super good. But the eventual goal would be to see if I could, using supervised or semi-supervised learning, beat Stanford ML group at doing radiology with machine learning. And the big deal there was they got 93% accuracy at diagnosing patients of pneumonia and a variety of other diseases that you can diagnose with a chest X-ray, which is a lot. It's like 10 in this data set. And so they actually got a machine learning model that was doing better than the 4 Stanford radiologists that they tested on. And I think it would be interesting to see if I could, maybe not beat them, but get anywhere close using way, way, way fewer labels or somehow leveraging interesting GAN characteristics. Another note about this, I think the fashion is pretty cool. I think the guy on the top looks sort of like an American colonial guy, whereas this gentleman here is more like London dude, you know, banker or whatever. But this guy's on the frontier, maybe. Anyway.
All right, with that conclusion, let's thank you for sticking around.
Thank you, everybody. Thank you. Kind of crazy.